which are really bad, and it's not convenient really bad. This is especially cool in the student with commodity. Those are that features. The features are into commodity price. This was for industry for market just going up. Okay, so make a prediction about which company? No, we are. It's all about correlation and the best commodity. No, we are looking for evidence. It's a mix. It's a strategy between both round and short in one industry, like where oil. So that is for company of 50%. But small company. I see all people are. So often just improve for some use fluctuation. So if I don't read how much percent could be okay, and yeah, it's a little long. So we will have some strategy.
Okay, hello everybody. Sorry to interrupt, but welcome to today's class. Hope everybody is doing well today. Today we are going to be continuing our discussion of linear regression. So you're probably finishing up the homework. Remember that that's due tomorrow. There are still, multiple office hours tomorrow if you need some additional help. Okay. So today we're going to be talking about a very important concept that we didn't get to a whole lot last time related to linear regression, which is overfitting and, sort of striking this balance between overfitting and generalizability. And we'll talk a little bit about how cross-validation is a powerful tool for that. And then we'll do a little bit more linear regression, thinking about how we can also include categorical variables into that model. Okay, so a little recap of what we did last time. So we started off with simple linear regression, where we assume we have in-paired data points. So our observations come in pairs, an explanatory variable X and a dependent variable Y. And we have N observations, and we are interested in investigating whether there's a linear relationship between Y and X. And our goal was to, sort of assuming that there is, find what that line of best fit is if we plot Y versus X find the equation of the line that best fits the data in the least squares sense. Okay, and we called beta 0 hat that optimal intercept and beta 1 hat that optimal slope. And so once we fit a line, then we have an equation of a line. We can plug in any x value into the equation of that line and get a prediction y hat associated with that x value. Okay, so the theorem tells you what those optimal coefficients are. And then we generalized this to the context of multiple variables. So in general, it's usually the case that we're not just predicting y from one single x, but we might have a collection of 5 or 10 or a number of features that we've collected, and we want to predict y as a linear function now of x1, x2 up through xm. Let's say we have m variables, once again, in observations. And so then we try to fit a model of the following form, where it's still linear in all of the variables, but we just have multiple variables. Now we can generalize this like we saw last time when we added an interaction term. Remember, we added two of the variables multiplied together, and that turned it in, well, it's still a linear model. It's linear in the variables, but it's not linear in the original variables. So depending on how you're thinking about that, you might call it a linear or a nonlinear model. But this is a way that we can include nonlinear relationships, which is really useful. So more generally, a more general regression framework would just be to model y as some function, a linear function, but of new variables that are obtained from the old variables in some way. And it could be in a nonlinear way, right? We could square the variables, we could multiply them together. So here these, this F1 through Fk are denoting potentially nonlinear transformations of the original variables that we started with. Okay, so that's kind of building up slightly more complex at a time. And there's several different packages to help with this. The stats models package is probably, the easiest to use for linear regression. It's what we mainly used last time. If you're doing cross-validation, the scikit-learn is helpful. So in general, the stats models, as is indicated by the name, is probably a little bit more geared towards the statistical framework. And the scikit-learn is a little bit more geared towards a machine learning framework, which is why there's more support for cross-validation. So good to be familiar with both of those. Okay, so let's go ahead and do our imports. Okay, and then, right, so these are kind of the two main functions that we went over last time. From statsmodels.formula.api, we're going to import this as SM. That's our stats models. And then we did the linear regression by calling that sm.ols. And then from sklearn, we're going to import linear model. Last lecture, we saw that we could then use that for linear regression. Okay, so let's look at some data, actually. This is going to be an advertising data set. So this is the data set that we were looking at last time, where we had 200 different markets. Think of this as different cities. And it was recording, how the sales for a product and relating that to the budget in each of the different media. So how much did you spend in advertising on TV, radio, and newspaper? And we tried a lot of different things, and we ended up settling on this is really kind of the best model. So this is including TV and radio as predictors, and also the interaction between TV and radio. Okay, so we can recall what we did there. And with that model, we got an R squared of 97%. Which was quite good. And we see that the p-value for the F statistic is tiny, tiny. So this model is definitely significant. And furthermore, if we look at the p-values on the individual coefficients, all of them are significant as well. So all of that is looking quite good. Okay. Okay, and so let's also just recap how we do the interpretation here. So in a particular market, if I spend an additional $1,000 on TV advertising, what do I expect sales to do? Okay, I'm going to scroll up to the output so you guys can take a look. So if I spend an extra $1,000 on TV advertising, what do I expect to happen to sales? Yeah, that's right. So, and here you have to remember that we were dealing in thousands, but yeah, exactly. But our units were in thousands. And so indeed, if you multiply this by 1,000, you get 19. So that predicts that sales will go up by 19 units. Yeah.
Is there the intersection? It has, the TV and radio, like the third, the fourth.
Yeah, this one here.
Yeah.
Yeah, I would say that interpretation is a little bit less straightforward than the individual one, you know, because it's saying if you spend an extra $1,000, like if you increase the product of your TV and radio budget by $1,000, you know, you're going to see this increase in sales. So that is a little, it's maybe slightly less straightforward what that's telling us, but it does seem to be telling us that that there's some synergistic effect, right? That these things interacting with each other is helpful. Okay, and then what does it tell us in terms of if we had to choose between TV and radio, what would we probably choose to spend our money on? Probably radio, yeah, because we see that we're going to get a bigger increase in sales. Okay, great. Okay, and then we also saw how we could plot this as a surface plot and read off the parameters of the model in terms of the intercept coefficients for the various media. Okay, I think we kind of went through all of that, so I won't spend too long on that. Okay, so a word of caution on overfitting. So we saw that when we included that interaction term, we fit it even better. And so it's tempting to just include more and more things. I think we talked about this a little bit last time. Let's square everything. Let's try all the different combinations. Let's throw everything in there. But this can be problematic. So a useful model is one that will generalize to data that it hasn't seen before. And so that is the idea behind overfitting and underfitting. So in general, in regression and other prediction problems, you want to develop a model on a data set that performs well on that data set, but not just on that data set. You want it to perform well on new data as well. And that when we say that a model performs well on data it has never seen before, that was not used to select the model, we say that the model is generalizable. So let's sort of see, let's look at an example here that can kind of help us understand these things. Let's say we have the following data set of black points. And here we're showing two different possible models that we could use to fit the data. The black one is just a simple linear model. Let's say we do linear regression and we compute the line of best fit. Now this blue one is a high degree polynomial. So you can actually fit any set of points if you use a high enough degree polynomial, and you can see that's actually what's being done here. This blue line is fitting all of the data points. Exactly. Okay, so let's pretend like this data set. We'll call this our training data set. And so we'll train the model using this data set. But then let's think about what's going to happen when we test the model on new data. So we can see, let's say that we have another point coming in and maybe we get it at like 3.0. That seems okay. That seems like quite possible. We'd get a new point coming in right here. Now the black line would be a pretty good prediction for that. But notice that the blue model would be really, really off. So if we think about new points coming in, the black model would do a pretty good job capturing the underlying pattern, but it might be really far away from the blue model because we're taking all of these like crazy turns to fit all of our data. Okay, so what's going on here is a phenomenon which you can think of as the bias variance trade-off. So we can decompose the error of a model into 3 terms. So we can decompose the error as a bias, plus a variance, and plus an irreducible error. Now the irreducible error is like stuff that you can never get rid of no matter what model you use. It's, say error in the data or things that you have no control over. So in general, we're kind of thinking about balancing these 2 terms, balancing the bias and the variance. And so the bias of the method is error caused basically by making the model too simple. For example, for this data, if you choose a linear model, you choose the black one, which is a straight line, you're forcing it to have a very simple structure, and you will not allow the model to, for example, curve if the data wants to curve. So there's going to be some error there because you've chosen an overly simple model. And that would be the bias error. On the other hand, you're going to have another kind of error, which is the variance. And this is how much the model will change if you collect new data, right? So if your sample data is replaced with another set of data. And so, for example, that's measuring when we have new points come in, how well is the model going to work for those? And we see that the blue model is not going to do well in terms of variance. When we have new points coming in, it's probably going to be pretty off. Okay, so this is kind of illustrating this trade-off, right? The black model has high bias but low variance, and the blue model has low bias but high variance. Did I say that right? I think I said that. Okay. Okay, so how are we going to select this in practice? Let's start off with an example and look at a certain data set and see how we can figure out a good way to do model selection. So we're going to look at an auto data set, which contains 9 features: miles per gallon, cylinders, displacement, horsepower, weight, acceleration, etc., for about 400 different used cars. So we can go ahead and read in the data. Okay, so we're reading it in with pandas like normal and just printing off what our different data types are. So that, .d types is quite helpful. And so here, most of it looks good, but we may notice that horsepower, which is a number imported as an object. And if you look at the data, you'll notice there's some question marks. So when that wasn't available, a question mark was entered, which is thrown off the data type. So what we can do is, first of all, remove the question marks, and then we can, on the remaining data, convert it to an integer. Okay, so we'll go ahead and do that, clean it up a little bit, and then we get the following data. Okay. And if we want to get, some summary statistics here, remember .describe is a great way to get basic summary statistics on your quantitative variables. So here we see all of the statistics for our quantitative variables, which is a good chunk of the data. And we're going to focus on the relationship between miles per gallon and horsepower. So let's take a look at the plot. So here we're just making a scatter plot of the horsepower versus the miles per gallon. What's the general correlation that we see here? Yeah.
As horsepower increases, miles per gallon decreases.
That's right. And so we call that what, a positive or negative correlation? That's a negative correlation, right? If as one increases, the other one decreases, we would say they're negatively correlated with each other. So like if we were to make a line of best fit, we expect it to have a negative slope. Although here, this doesn't look quite as beautifully linear as the data that we looked at last time. Okay, I don't know that the data that we looked at last time was beautifully linear either, but here you see that curving pattern pretty strongly, which makes you think, I don't know if a linear model is quite the best model for this. So let's try some different options. So one of the simplest things that we could do is just try some different polynomial models, right? We tried a line, we could try a quadratic polynomial, we could try a cubic polynomial, you know, just increasing the degree of that polynomial and see what kind of fit we get. Okay, so let's try it. We're going to consider the following linear model where we're going to model miles per gallon. Okay, and now here we're just making a polynomial, a higher degree polynomial from horsepower. So this fits into the framework that we were talking about of like creating new variables and doing linear regression on those variables. But note here, it's all coming from that one underlying variable, which is horsepower. This is just a polynomial. Okay, so we might think that choosing a large M, choosing a high degree polynomial would be a good thing. We could really, you know, we have so much flexibility, we can get it to curve any way that we want it to curve. But well, but that's going to be the catch, right? But can we do that without overfitting? So let's try it out. So so first of all, we're gonna make a handful of models here. So our first model is just going to be the linear model, just like we did last time. And then we're gonna run that with the sm.ols from stats models, and then we'll pull out the parameters in a dictionary. And then our second model, so here's the syntax for that. We did not see this last time, but I mean, yes, you could just define this new variable in your data frame, but you don't have to. You can just use this syntax horsepower plus horsepower squared, and it'll do that regression, including the square of the variable. Okay, and then similarly for the third model, we'll have the variable, its square, and its cube, and similarly for the fourth. Okay, and then we're just going to make a scatter plot of the data, and then on top of the scatter plot, first we'll start off with a grid of points, grid of x values, and then we're going to compute the y hats, right? So for each model, we're going to compute the associated y hats. We need to know the parameters of the model for that. So we're going to access the parameters of the model and make that transformation, well, evaluate the model on the points x. Okay, and then finally, we'll plot all of these different polynomial models now that we've actually computed the y hats. Now we'll just make a plot of the x versus the y hats. And we'll take a look at this. Okay, so so in the plot, you know, the black points are just the scatter plot, but all of these lines, those are just the plots of x versus y hat for the various models. Okay, and so we definitely see that these higher degree models are curving to fit the data, so that may seem good. With the fourth degree polynomial, it's kind of veering off here, which may be a little troublesome. We don't know where it's going. Okay. And if we check out the R-squared values for all of these models, we'll see the following. For the linear model, 0.6. For the second degree polynomial, 0.687, then 0.688, then 0.689. So what do we see here? Well, that is very true. We do get diminishing returns as we increase, really beyond 2, we're not getting very much. We're getting a tiny bit, right? Like it's not going down. It's still increasing, but it is indeed really leveling off and giving you diminishing returns. Okay, but this will always happen as you increase the complexity of your model and you fit it to data. The R-squared value, it can never go up. It can only go down. So you can only decrease it by increasing the complexity. But let's check out what kind of p-values we get when we do that 4th degree model. So here, we're looking at our 4th degree polynomial, and we've already looked at the R-squared. We get overall a p-value that's significant on the test as a whole, looking at everything all together. But then if we look at the individual coefficients, a lot of these p-values look very large, right? So we're getting a lot of really large p-values on the coefficients in this model, which is generally not a good sign, right? Okay. Right, so for m greater than 2, we see the p-values are very large and we don't have a strong relationship between the variables. So, one philosophy is Occam's razor, which is to say, well, the simplest model that gives good performance is the best one. So that's kind of, basically what you were saying about diminishing returns. One thing that we could do is just say, well, let's choose the model where it levels off. We can, as we see the increase in the R-squared, it's quite clear that maybe choosing a 2nd degree model is a good idea because we get a nice boost from that and then it levels off. So that's one thing that you could do, kind of the Occam's razor approach. But there's actually an even more rigorous way to approach this problem, and that's via a method called cross-validation. So what is the idea with cross-validation? Cross-validation, it's a very nice approach, which is basically an experimental approach. So let's say you're given a data set and you're going to split it into a training data set and a testing data set. You're going to split it into 2 parts. And then you're going to build a model only looking at the training data set. Build a model just based on the training data set. And then you're going to apply that model to the test data set and evaluate the performance on the test data set. And then you can do that for a bunch of different models, try out linear, try out quadratic, try out really high degree polynomials, whatever models you want to try them all out and compare their performance on the test data set, and then pick the model which gives the best performance on the test data set. Okay. Yeah.
Are you preparing the training data set at the beginning, or you keep collecting the
so like, do you have all of that data at the beginning of your process?
Yeah, for the testing data set,
Mm-hmm.
are you going to prepare all of them at the beginning, or are you going to keep collecting them?
I mean, I guess it can vary, like data collection procedures, but what I'm envisioning is you have one data set and that's all you have, and you're not going to get more. So you're just going to hide a portion of it and pretend you didn't see it and use it for model evaluation.
Okay.
Does that make sense?
Yeah, even though there's new data comes out, every second, you're not going to add them into the data set.
I mean, not in this simplest framework. We're not considering data coming, I mean, I'm sure you can do generalizations about how should you do cross-validation in real time, but in the simplest context, we're not thinking about new data coming in real time. We're just, we have some data that we've collected, and we're going to split it into two parts. Other questions? Oh, I've got a couple in my chat, so let me see. Okay, great. They answered the question from a while ago. I'm sorry, I just saw the chat. But please do continue to post questions or answers. Okay, so this makes a lot of sense. An important question is, well, how should you split it? Should you do 50-50? But if you don't have a very big data set, that might be throwing away a lot of data that would be relevant for building a model. So usually you don't want to do that. Usually you want to keep more for training, a bigger portion for training and a bigger portion and a smaller portion for testing. And, you might also think like, well, maybe our results could depend on the way that we split the data. Maybe we had like a couple of outliers, and depending on whether those outliers got put in the training data set or the testing data set, we got really different results. And that can be true as well. So there are generalizations where you can, repeat this partitioning procedure multiple times so that every data point kind of takes a turn being a test point and a training point. But for now, we're not going to go into, those setups. We're just going to start off thinking about, we have one data set and we split it into two parts.
Wouldn't just a quick question, wouldn't things like that be biasing your data and your training data set, or your model, if you were cherry picking data points that you wanted to include or not include in your model?
Yes, it's important that whatever process that is still random, right? But you could, so one thing that you could do, for example, let's say you're going to split your data set into three parts. You split it and you have like 2/3 of it that you train and test. But what you could do is you could kind of take turns. I'm going to train on parts 1 and 2 and test on part 3. Then I'm going to train on parts 2 and 3 and test on part 1. And then I'm going to train on parts 1 and 3 and test on part 2. And then I'm going to aggregate all of those results into one like evaluation for that model, if that makes sense. And that way, if you do have outliers, you're making sure that you're trying, all the different possibilities of what could happen. Does that make sense? But you would still want to do that allocation like randomly.
Yeah, totally got it. Yep, that makes sense. Thank you.
Okay. So let's see. Okay, so where did I leave off? Okay, so what we noticed when we did this example is that as we increase the complexity of the model, the accuracy on the training data set is always going to increase. That has to happen. But the question is about what's going to happen on the test data set. Usually what will happen is increasing the complexity is useful up to a certain point, and you'll see the test error decrease up to a certain point. But then if you make the complexity too high, it'll start to overfit and you'll see the error start to go up. And you want to kind of find that sweet spot, which is the minimum of the test error. Okay, so let's see how we can do this for the auto data set. And there's a scikit-learn package for cross-validation that is really useful. And so we're going to use that instead of stats models so that we can do cross-validation. Okay, so we'll start off creating a linear regression object. And now we are, okay, so now we don't have quite that nice functionality where we didn't have to explicitly make the columns. Now we have to explicitly make the columns. So that's what we're doing here. We're going into our data frame and we're just adding in the columns, which is the horsepower raised to various powers. That's because we're not using stats models. Okay, and then now with scikit-learn, we also, it doesn't work as well with the pandas data frames. We have to extract the values from the pandas data frame. So we'll just have our X, which is the extracted values of the explanatory variables, and Y, which is our dependent or response variables. Okay, so this is actually now a NumPy array, which will play nicely with the with this LR framework. Okay, so then we'll plot the data, and then what we're doing here, well, let me just scroll down to the plot so you can kind of see what's coming, and then I'll scroll back up so you can see, right, so we plotted the data, and then what do you see? We see all of these different polynomial models here. Okay, and so what we're doing here is we're doing a linear regression where we just look at the first M columns of that data. So that's the, however, we're going to increase the M, and then we'll include more and more of those powers. And then we're going to do a linear regression, and then we'll plot what the predicted values are for that model. And that'll give us the different lines. Okay, so this is what we get. And here we haven't done any training or testing data yet. This is just illustrating with those tools how you would do the linear regression for the different models. Okay, so now let's see how we could repeat something like this, but with cross-validation. So one really useful function is the train test split function. And this will split the data set into training and testing. And also the score function will give you the R² value of the prediction output by the model. So basically of your Y hats according to the model. Okay, so we're going to try it. Since this data set is not very large, we're going to take the training data set to be 90%, just so we can illustrate the point more clearly of what's going on. That's a little bit high. Normally, you'd probably see more like 70 or 80% for your training data, although you may see, different approaches in different contexts. But just a little warning that 90% is a little bit of a high percentage to use for training, but it'll illustrate the point. Okay, so first we need to import this function, which is train test split. And then we tell this function, okay, this is our data, our explanatory data, and this is our response data. And we're going to do a test size of 0.9. So we're going to do 90%. Oh, sorry. Test size of 90%. Okay, I'm sorry. I thought I had it backwards. I thought this was doing a training size of 90%. Right. Okay, this is doing a test size of 90%. I forgot that it was doing that much for the testing. But this will really illustrate, it'll illustrate well sort of the phenomenon that can happen. So let's stick with this. Okay. And then we can plot the data. Again, let me scroll down to the plot so you can see what's happening here. Okay, so we have the training data in red and the testing data in black. So indeed, in this setting, we see that it's a small percentage of the data that's being used for training, just 10%. And then these are the different models that were computed just from the red points. Okay, so these will look a little different than what we saw before when we did these same models, but based on all of the data. Okay, let's see if there's anything in the code that I want to point out. Just the score function, right? So what are we doing? We're looping over all the different models. We're fitting a linear regression model with that complexity. And then we are applying this lr.score function to evaluate both how it's doing on the training data and how it's doing on the testing data. So those are kind of the key aspects of what's going on here. And we're plotting those predictions to make the line. Okay, so what do we see happening? For the low complexity model, we get an R squared of 0.65 on the training and 0.58 on the test. And then you can take a look, as we saw before, as we increase the complexity, the R squared on the training can only go up. It cannot go down, it can only go up. It does level off, just like we observed when we did the modeling on the whole data, same type of pattern. But what does it look like in the testing data? What do you think would be the best model choice based on this experiment? What's that? Any other? Why do you think 3?
Oh, never mind.
That's right. So they're very close, but this one's a little better, right? And also less complex. Yeah.
So I'm noticing we have the same exact values for these. So is the split, is that not random?
So what did you rerun the code, or did you like just open the notebook?
Well, I did run it, but I'm just noticing you put random state equals 1, so that probably being random.
Yeah, right. So that's just maybe helpful so that we can all see the same thing and come to the same conclusions. But indeed, in general, if you take that out, then I think you'll see slightly different results. Yeah, good question. Okay, any other questions on what we've done so far? Okay. Okay, so as we increase complexity, accuracy of the training increases, but the generalizability, well, it usually increases a little bit, but then it decreases after a certain point. So it's looking like that second degree model is best overall. Let me do a little time check here. Okay, that is probably a good break point. So let's take our 5-minute break and come back at 4:25. Hi.
It's me again. I don't know why, but I cannot update my Jupyter notebook. It said, oops. Oh,
Misspelling of that.
okay. After that, and I. Yeah, there's no linear regression too.
Weird. Did you guys were able to access the 10th lecture, right?
Oh, I think
Yeah.
is the get pulled out?
Yeah, I did get all.
What does it say?
It says
Okay, yeah. So basically, either you or she changed this, and so it's trying to pull those and saying it's conflicting with yours.
Oh,
So you want to go into your like file explorer. Sorry, I'm in Windows. So I have no idea.
Yeah.
You want to go into your file explorer and then just rename this file. Yeah, just a lecture file from this one. I just add my name to it.
like oops. Which one?
Yeah, that's right. And then in folder 9.
Um,
Yeah, so in folder 9.
So you can just call it like old or something.
And then yes, there.
this one?
Yeah,
So rename it.
yeah. I just put like my name on it. You can do anything with it. And that basically just says like this is separate from the Git project.
Oh,
So when the Git push work.
so
Nice.
okay, cool.
Thank you so much.
Thank you.
I didn't think I changed anything, but who knows?
I don't know.
Maybe I did. Okay, and we have another comment that the change to lecture 9 will cause a conflict. Okay, I did make a change to lecture 9 because we discovered a mistake, right, when we were going through it. And so I forgot about that. Yeah, I was thinking of just of lecture 10, but you mean the lecture 9. So I did update a lecture 9. So what you want, so maybe you're getting a conflict. I mean, and it's not a big deal. I didn't make a whole lot of changes, but I would recommend that you go in and just rename that lecture 9 Jupyter Notebook, put your initials on it or call it old, and then do the git pull again. And then there shouldn't be a conflict because there won't be any file with that name when you do the git pull. Okay. We do try to avoid making updates because this is really annoying, right? You shouldn't have to do that. But unfortunately, with Jupyter Notebooks and version control, it does not know how to integrate, Jupyter Notebooks together. Okay, does that answer your question? And I'll keep that in mind in the future with, okay, is this really worth updating the file to fix a typo? But it was, yeah, they had the hypotheses were wrong, so I thought we should fix it. Okay, why don't we go ahead and get started again? And I do want to save some time for the activity because I think it'll be really helpful just for you to get a few minutes to play around with doing one of these regressions. And the data set that you're going to be looking at is a credit card data set. And you'll use stats models to study this data set. So this data set consists of about the information collected from about 400 people. And well, I'm sure you're probably all familiar with the idea of credit card. You use a credit card to buy things and then pay for it later. But with every credit card, there is a limit set by the bank that's issuing the card, saying, well, what's the maximum amount that you can charge to your card? And so one question that people might be interested in answering is, how should you set that limit? And generally that's, very closely related to your credit score. So, your sort of financial history and income and all that is evaluated, and you're given a credit score. actually, I'm not 100% sure if the income goes into the credit score. I know they're correlated, but I don't know exactly how they compute the credit score, but then your credit score kind of determines the limit that you have on your credit card. Okay, so we're going to use some regression tools to study this data set. And ideally, we'd like to understand what factors determine credit ratings and credit limits. And so this might be of interest to a bank that wants to protect its assets, or it might be of interest to an individual who, say, wants to buy a home and wants to get as high a credit score as they can because it'll lower their interest rate. And there are certain things that you can do to kind of, game the system, well, not game the system, but affect your credit score. Okay, so one thing that we haven't seen before is how do we incorporate categorical variables into a regression model? And we'll look at that a little bit as well. So first, let's take a look at the data. So we're reading in this credit.csv file. And so we see here income, credit limit, credit rating, how many credit cards you have, your age, your education level, genders, whether you're a student, whether you're married, ethnicity, and balance. Okay, so first of all, let's just do some summary statistics and take a look at what the data types are. So when we run this, we see these are all numeric, float, ints. These are all objects, but that makes sense because those are categorical variables. Looks like education was recorded as an integer because there's some kind of order, high school, college, master's, PhD. So that overall looks okay. And then we see the data is pretty evenly split between male and female, about half and half. 40 students out of the 400, and a little over half of the people in the data set were married. And we see about half of the data was Caucasian, and then about a quarter Asian and a quarter African American. Okay, so just recapping the column names, which we see in the data frame. What do you think about the income? Does that look right? So we're seeing a mean of 45. Or what do we think the units on that probably are? Probably thousands, right? Because 45,000 sounds probably about like a mean income. So why it's showing up that way, who knows? Maybe because it was a comma separated file, the commas were denoted with periods in the file. So that's something like that could be the case, or the data's from Europe or something along those lines. But we're pretty confident that these should be interpreted as thousands. And so one thing that we can do is just, multiply everything in this column by 1,000. Okay, so that's what we do here. We're just going to call the .map function, which which maps x to 1,000 times x. That's going to multiply that whole column by 1,000. And so now these incomes look like actual annual incomes in dollars. Okay. So one thing that's helpful to look at when you're in the exploring the data phase are the covariances in the data. So how the variables vary together. And we've talked about two ways of doing this. One, more quantitative, where we compute the correlation coefficient between all the different pairs of variables. So we get that matrix, that correlation matrix, which for every pair tells us the correlation between the two. And then another way is visually, we can just plot every different pair and see what it looks like. And that may be helpful because you might also notice some nonlinear patterns when you do that, that you didn't detect when you just looked at the linear correlation coefficients. Okay, so here we see our correlation matrix. Anything that kind of stands out to you in looking at the correlation between these variables?
Rating and limit are really highly correlated.
That's right. Rating and limit are really, really highly correlated, 0.9968. So what is that telling us? Yeah, and they're essentially the same thing. Like your credit score essentially is your limit that you're given on your card. So if we understand one of those variables, we kind of understand the other one. So this shows us that they're essentially identical. I guess there's some tiny differences somewhere, but they're essentially identical. So those we can almost just think of as being like the same variable, but then we're kind of interested in, you know, how the limit or the rating, depending on how you want to think about it, is affected by the other variables. Okay, and then here's the plot with all of the different scatter plots. And so indeed we see, you know, those two, they're just like perfectly correlated. And then we see strong correlation with income, right? So this is income and limit, and this is income and rating. So that looks like a pretty strong correlation. Some of these do not look very strong. Anything else that you, so the limit is in the second column. So if we kind of focus on this for a second, what else looks like it might be important for limit? The balance, yeah, that one looks pretty correlated with it as well. Yeah, some of these just kind of look like nothing really informative. But, you know, sometimes it doesn't look informative when you look at it like, you know, pair by pair, but it still could be having some useful information hiding in there when you combine it with other variables. You don't know for sure, but the correlations do kind of stand out. Okay. Oh yeah, and then one other thing, we see some weird stripes here. Why do we see weird stripes in some of these plots?
Those variables are continuous.
Yeah, right. Those are the discrete variables. So we're not going to get this like total scatter. You know, we're going to have our values restricted to specific points. Yep. Okay, and this, notice what we're doing here when we ask it to give us the correlation matrix and the correlation scatter plot, it's only looking at the quantitative variables. The categorical information doesn't appear. You can't do a scatter plot with categorical information, but we may want to have some way of visualizing what's going on with the categorical variables. So how can we do that? So here I'm just showing you basically two different things that you can do. One is for each categorical variable, you can do the dot value counts, and then you can plot those with the bar plot. So this is how you would make bar plots of the categorical variables. And I think this was relevant for the homework assignment, which is due tomorrow, because I don't think we'd had an example like this yet, but there was a question where you had to get like multiple plots to show up on the same axis. And so here's this might be helpful for thinking about that. This is exactly kind of the same thing going on, where we're having like these four different plots that we're plotting at the same time. Okay, that was just a little side note. So let's look at the bar plots. What do we see? Gender, pretty even. A little bit more married people than single. Not very many students. And sort of this split of the ethnicities. Now, what we're really interested in though, okay, we might be interested in knowing, you know, the demographics of our data set, but we want to know how it's going to affect your credit limit. And so we want some way of kind of relating the continuous variable that we're interested in with a categorical predictor. And so a box plot is a nice tool for that, because you can break up your data into the different categories. So for example, here, this is the values. This is basically summarizing the distribution information of the limit variable for males and of the limit variable for females. Are you guys familiar with what a box plot is? Yeah, okay. So the box plot shows the median, first quartile, the third quartile, and then what is it? These little dots up here are the outliers, and it kind of draws the little bars. So it just gives you a little bit of a sense of the spread of the distribution. And so we can, compare the medians here. The median for female looks a tiny bit higher, but they look similar. Okay, and so here you can sort of see similar plots. Yeah, a lot of these, however, to me, a lot of these distributions look rather similar. We don't see really strong patterns in these plots about one of these things is really, shifting the box plot. Okay. All right, so in the last few minutes, I'm going to talk a little bit about categorical variables, how to incorporate them into your linear regression, and then save some time for the activity. Okay, so as we've seen here, we have 4 categorical variables. We have gender, student, married, and ethnicity. How can we include them in a regression model? Well, you have to make them a number, because you can't make an equation out of a string. But one thing that we could do is we could create a dummy variable that basically turns gender into a number. So we could create the variable gender number, which is 1 if the person is female and 0 if the person is male. And then we could try to fit a model of the form. We have some thing we're trying to predict. For example, let's take income. And then we, again, have a linear function on the right-hand side. I will say, normally, you probably wouldn't do this if the categorical predictor was the only thing you had on the right-hand side. Normally, you also have continuous variables in there too, and then you throw this in as something additional. If it's just a categorical variable, this doesn't, it's not really going to do a whole lot, but it can be helpful in addition to other things. But you can run it like this, and I'll just show you how to do that. So first, we're going to create our dummy variables. So we're going to create a new variable, gender number, which we're going to obtain from gender by mapping male to 0 and female to 1. And we can do the same both for student number and married. So we're just creating these dummy variables, which are binary and indicate the value of the categorical variable. Now that we've done that, we can run a linear regression. So for example, let's predict income as a linear function of the gender number and see what we get. Okay, a terrible R squared, right? So we got a really bad R squared. We did get a very large p-value there and a very large p-value there. Okay, so what we're getting is not significant. So one way we could interpret this is that gender is not a significant predictor for income. If you were interested, though, in just analyzing just that question, what else could you do of the statistical tests that we've talked about?
A 2-variable t-test?
Yeah, exactly. A two sample t-test, right? So in that case, you have two samples, you have the males, you have the females, and then you have income recorded, for each group. And so you could compare the means with the two sample t-test. So that would be more appropriate for this example, but it's just illustrating how to include it in a linear regression. Yeah.
How do you know whether you should do a Z or a T again?
So basically, if you're doing it on quantitative data, they're quite similar, but if you have a small sample size, you definitely want to do a t-test. So a z-test can be unreliable for small sample size. So if your variable is quantitative, it's probably safer just to do a t-test because it's fine either way. The z-test, though, if you're comparing proportions, like one of the examples in the homework and some of the other examples we did, with the proportions, it's always a z-test. It's just like a different setup and a different distribution that you get there.
Okay.
Okay. All right. So we see this linear regression. Okay, now we could get even fancier. What if we have a categorical variable with three categories, like the ethnicity variable, because we had Caucasian, Asian, African American. So one thought might be, okay, we can make a new dummy variable and we can just record it as 0, 1, 2. What would be wrong with that?
If someone is African, they will get 2 in this coefficient. It's just like 2 Asians.
Right. So yeah, there's really not an order associated with ethnicity, at least not one that makes sense, right? So indeed, it doesn't make sense that an African-American person should be like more similar to an Asian person than to a Caucasian person. Like, why? That's totally arbitrary, right? So with categorical variables, in general, there's, sometimes there might be a relevant order, but most of the time there isn't. So what do you do in this case? Is you have to use more than one dummy variable. So one variable is not enough. But what you could do is, make an Asian variable that's just one if the person is Asian and 0 otherwise, a Caucasian variable that's one if a person is Caucasian and 0 otherwise. You could do the same thing also for African American for your third category. It's not actually necessary because if you think about to encode a binary variable, male, female, I just need one variable that's 1 or 0. And then if you want to encode 3 categories, you can encode those as like 0, 1, 1, 0, 0, 0. So I think in general, you only need one less dummy variable than the number of categories that you have. Okay, so let's see how we can actually create these dummy variables. There's a nice pandas function called getDummies. And so when we use that function and then concatenate to our data frame, now we can see it's actually made a dummy variable for each of the ethnicities, African American, Asian, and Caucasian. Okay. And yes, so this is a great little ending comic. I don't know how to propagate errors correctly, so I just put error bars on all my error bars. We should probably do that more often. Okay, so let's see. We've got okay. I don't think that's a question. Any questions before we do the activity? Okay, I'll just give you a little preview here of what you're going to do. Right, so here's the activity. Okay, so you're going to be looking at that same data set, which is the credit card data set. And first, you're just going to do a simple linear regression. Okay, and then you're going to do a more complicated regression with multiple quantitative variables. And then you'll finally try putting in some of the binary, we'll just worry about the binary categorical ones. Okay, so why don't you find a partner? If you like, it's always nice to kind of see how somebody else does something, and I will start the breakout rooms. Okay, so we've got 17. Okay, have fun. Whoops. Okay, any questions? You all right?
Yeah. So, just
Trying to get the
Yeah.
checks for it. Yeah, where's the data set?
It should be in the folder. I sure hope it's in the folder.
Oh,
It's the.
Yeah, it's the credit one.
okay.
It's the one that we were using in class. The one, so what I was talking about it in the lecture, you're gonna use that same one.
I was trying to get it from the website of the assignment. Okay.
Yeah, no, so you, yeah, you don't have to do that. Right, so I mean, this code right here is already in the activity. It's gonna read it all in for you, just like we did in lecture. So just run that cell and it should be fine.
Yeah, I'm trying to import it to Colab.
Oh. Yeah, that I'm not sure about.
If you have to read the file in the collab, there's like special collab functions you have to use.
Yeah, I just had to manually upload it.
That's good.
So if you don't specify anything for the OLS function, does it assume that the null hypothesis will be that there's just no effect?
So like in which?
Like I just ran this OLS function here. It's like, what's the null hypothesis? So that would be for this schema, right?
Right, for the p-value of the mean.
So what is the null hypothesis of the default?
The default is that there is no linear relationship. And the alternate is that there is a linear relationship. And we quantify that in terms of the value of that coefficient. So the null hypothesis would be that that coefficient is 0.
Okay.
Yeah, but like beta 1, I guess, in that context, beta 1 equals 0 would be null, and beta 1 not equals to 0 would be alternate, and is defaulting to a two-sided alternate.
What is the job fit? I'm asking because I didn't know what the error was, and I wanted to know the previous weeks.
So I think we did that with the LR. Okay, so I don't think you don't want to do that.
Okay, I don't need next year.
No.
Is that just like format the data in a way that makes it easier for like the S and the OS? I guess
Well, we have these two different like frameworks. We have stats models way of running linear regression, and then we have a scikit-learn way of running linear regression. And so I think that the dot fit was how we ran the scikit-learn way,
Oh, okay.
but you don't need it for the OLS way.
Okay.
It's just like a different package.
The scikit-learn is like not like pandas.
That's
right. Okay. All right.
It doesn't want to.
Okay.
But it's nice for cross-validation, which
Yeah.
is, yeah, kind of what we were doing both.
So the second question is just let us find it's almost
Um, So for the second one, yeah. So start off probably just throwing in all of the quantitative ones.
Okay.
Leave out the categorical ones, and then seeing like, are they helpful? Which ones should you take out, basically? Which ones are not helpful?
So maybe.
Probably you just want to do it interactively. I mean, maybe you could write for you, but that's not necessary. I mean, you can kind of play with it and see what you think is a good model. Still getting there when you have it.
Yeah, it's just a sales. So.
So it's not sales. Your limit.
Oh, okay. I don't know why I changed that.
Okay.
This is. So. This does.
Oh, wait. Hold on, did I misremember about the fit thing? I'll go back and check this in class, 'cause maybe I told you wrong.
Oh, no, it's the thing. Yeah.
Yeah, I'm sorry. That is there. I got mixed up. Yeah, I think it should be there. I'll put up the example here just as a little, so it should look very similar to that. Sorry. You do have the dot fit.
Are we going to learn further?
No, not so much. We're gonna kind of switch gears. This is about what we'll do for linear regression. And then next week, we're actually gonna talk a little bit about ethics in data science. And then Professor Wong is gonna take over and do a number of lectures on data visualization.
Okay. I went to Professor Wong lecture last year, and he's talking about SB on YouTube. I'm pretty afraid about this. I have no idea.
I think she's gonna sort of do it for like 2 weeks though, so it'll be nice
Yeah.
chunk of time to get through it.
Yeah, they put Professor Wong with the one. All the way to SB. I dropped
And SVM will do actually later in the course. So the initial data visualization, that's how to do it. So feel free to stay and work on this as long as you like, but it is 1 minute after. So if you need to leave, feel free. I did think it's just good for you to get a little practice with this because there's a little bit of an art to like, making the model. Yeah, usually you start off by throwing everything in there. And I mean, there's different strategies, but one way to do it is throw everything in there and then start taking out the things that aren't helping. Thank you.
Yeah, you're welcome. Have a good evening.
Hi, Anna.
Hi.
Yeah, may I ask a few questions?
Yeah, absolutely.
Yeah, so like I'm just not still not super sure about like the p-values for in both hypothesis testing and the linear regression. I mean, what does it mean like exactly?
Yeah, so here, let me see if I can joining a room will stop your screen. That's now I'm muted. Hi, Ling. I'm sorry about that. I think I was trying to join your room and I went into the wrong one. So what was the question?
I mean, just the p-values in both hypothesis testing and the linear regression. I mean, what does it mean exactly?
So what did the p-values mean in the context of the linear regression?
Yep.
Yeah, okay. Well, first of all, do you know like what the null, so to answer what the p-value means, you kind of have to know what the null and the alternate hypothesis are.
Yep.
So what would be the null and the alternate hypothesis in the hypothesis test that happens when you run the linear regression? There's basically going to be two different hypothesis tests going on, like a global one, and then one for each individual coefficient. In the global one, the null hypothesis is going to be that all coefficients are zero. All of those coefficients are zero. So there's like, no linear relationship between anything. And the alternate is going to be that at least one of the coefficients is non-zero. So that's like the null and the alternate for that F test that you see the p-value for. But then you also see the p-values for the individual ones. And sometimes that's even more useful. And so for the individual ones, the null hypothesis will be, say, beta 1 is equal to 0. And then the alternate will be beta 1 is not equal to 0. And in words, that would be saying the null hypothesis would be that there's a linear, so the null hypothesis would be that there is no linear relationship between X and Y. And the alternate hypothesis would be that there is a linear relationship between them.
Yes.
Does that make sense? So then,
yeah.
Right. So then with the p-value, if it's small, if it's like less than 0.05 or it's less than 0.01, you're going to reject the null hypothesis, which means that there's significant evidence for a linear relationship. It looks like there really is a linear relationship in the data. But if the p-value is large, then you cannot reject the null hypothesis. So if the p-value is large, there is not evidence of a linear relationship.
Okay, I see. So I know how to use them. I just wondering, like, so p-value is actually a probability, right?
Correct. It's the probability, assuming, if you assume the null hypothesis is true, it's the probability of observing something as extreme as what you observe in your data.
Okay, all right. Oh,
So it is a probability, but it's a probability computed under the assumption that the null hypothesis is true. So it's like, if this were true, what are the chances that I would see what I'm seeing? And if they're really small, then we start to kind of rethink the assumption.
Okay, cool. That makes more sense. Thank you.
Yeah, you're welcome.
I have a somewhat related question about like linear regression with multiple variables. So when you're interpreting the coefficients, what if the scales of the variables are completely different? Don't you have to standardize or normalize the scales first in order to compare their coefficients?
Yes, so you can compare their p-values, and that'll give you a good sense of like the most important ones. But you're absolutely right that if you have not scaled the variables, the magnitude of the coefficients may be meaningless. You know, if you don't know that things are measured on a similar scale, then yeah, the magnitude of the coefficient may not tell you anything at all.
Okay, and then when you get to more and more complex models, so not just like linear regression, things that are way more complex, do p-values still hold up there? And what would a p-value or a null hypothesis be for that? Like if you're not doing a linear relationship between something, you're trying to find some non-linear relationship between two variables?
Yeah, well, I mean, I guess we saw some examples like that too with the polynomial model, where we started off with a variable and then we built these like nonlinear transformations of it. And then we ran linear regression like normal, and it's still kind of giving us a p-value for each of those nonlinear transformations of the variable. So you could still kind of interpret it in a similar way. Yeah, but it's like a little, I guess the interpretation might be a little more awkward, like the square of a variable has a linear relationship with the response, but that might still be a hypothesis that you're interested in.
Okay, yeah, that makes sense. Thanks.
Okay,